This is E4.2, which is logarithmic functions and graphs. Okay, so the reason we care about logs is logs are the inverse functions of exponential functions. So remember when we went over inverse functions back in like 2.8, I think, remember we would swap and solve. So I'm going to write some stuff down. You don't have to write this down. I'm going to erase it. If you had something like, I don't know, y is equal to the square root of x. Okay, we would swap and we would get x is equal to the square root of y, and then we would resolve it for y. So here we would get x squared equals y, that kind of thing. And then this is the inverse function. So like a square and a square root are inverses. Okay, and that worked out nicely for us. Now, when we deal with exponential functions, okay, exponential functions look like this right here. So they look like y is equal to a to the x power. So if I wanted to find the inverse of y equals a to the x power, if I were to swap here, I would end up with x is equal to a to the y power. And you remember once we swap variables, we resolve it for y. Now here, we don't have a way to solve this for y. We can't take like the y root of both sides. That doesn't solve it for y. We can't divide off the y because it's in the exponent. We can't raise both sides to the 1 over y power. Okay, that doesn't get y out of the exponent. So what we did is we use logarithms, define logarithms to be the inverses of exponential functions. Okay, so what we're going to do, I'm going to go ahead and put this down here. Using the swap and solve method, we know that the inverse of y equals a to the x is x equals a to the y, just by swapping variables, just like I did above. I'll go ahead and erase that. Okay, so what we're going to do is we're going to define a logarithm to be the inverse. Okay, so it says let a be a fixed positive real number not equal to 1. The logarithmic function with base a is defined to be the inverse of the exponential function with base a and is denoted log base a of x. Okay, so in other words, as a note here, x equals a to the y, which is what we just said above, would be the inverse of an exponential, okay, is equivalent to y is equal to log base a of x. So what I want to point out here is notice in exponential form and in log form, the exponential base is the same as the log base. Okay, so all we're doing is swapping our variables, right? And we're using a log base a rather than an exponential base a. So that's our connection. Okay, so let's go ahead and look at some logs that we're going to be using, and I'm going to go ahead and write down here. We can go both ways. We can go from an exponential to a log, or we can go from a log to an exponential. So here it says, so the inverse, excuse me, the inverse of y equals x to the a, or f of x equals x to the a, would be the log. Okay, so f inverse of x equals log base a of x, because log base a gets rid of exponential base a. The same is true, we go the opposite direction. Okay, if I start out with log base a, or f of x equals log base a of x, then that inverse would be a raised to the x. Okay, so log base a and exponential base a cancel one another out, just the same way that like a square and a square root cancel one another out. Okay, so let's go ahead and look at a couple of the general forms of logs. If you notice on your calculator, you have two buttons. You have a button that just says LOG for log, and you have a button that says LN, not NL, LN. Okay, these are the two buttons you have on your calculator that we use for logs. One is called the common log, one is called the natural log. If it's a common log, it is base 10. Now, when its little base is 10, we don't write it for whatever reason. That's called our common log. So anytime you see something written like log of x, if there's no little base there, it's an implied 10. Okay. The second one is a natural logarithm, which is when the little base is e. Okay. When the little base is e, excuse me, when the little base is e, then we don't write it as log base e. We write it as just ln x. Okay, so when you see ln, know that ln is the same as log base e. Okay, and e is just the e button on your calculator. It's roughly like 2.71 something. Okay, so we'll see both of those. So let's go ahead and look at defining, I'm sorry, not defining, simplifying a log given the definition. Okay, so this is what we define a log to be. Log base a of x equals y. Okay, so if I want to go from log form to exponent, well, I'm not going to do it that way. Let's just use the definition. So here we have log base 2 of 4. So I'm going to, just like the definition here, set this equal to y. Now when I set this equal to y, I can use our exponential form to get rid of the log. Okay, remember we talked about logs and exponentials are inverses. So here, if I want to get rid of log base 2, I'm going to use an exponential base 2, and I'm going to raise this equation up into the exponent. The reason why is, remember we did, I think in 118 the other day, we did something like if 2 to the x equals 2 to the 1, then I can cancel the 2's, and that just means x equals 1. Okay, we're doing this roll backwards. We're starting out with an equation, and then we're putting in an exponential base and moving that equation back up into the exponent. Okay, and this is fine as long as we do it on both sides. Okay, and here I'm specifically using 2 because I know that exponential base 2 and log base 2 are inverses. So those will cancel, and notice what I'm left with is 4 is equal to 2 to the y power. And now we should be able to figure out what y is, because notice 4 and 2 can both be written with an exponential base 2. 4 is the same thing as 2 squared. So 2 squared equals 2 to the y power. And then I can drop my exponentials, which means that y equals 2. Okay. Same thing on this next one to the right. I'm just going to set it equal to y using the definition. And then I'm going to use the fact that logs and exponents are inverses to get rid of log base 3. To get rid of log base 3, I'm going to use exponential base 3. And I'm going to raise my equation up into the exponent. Okay? Because if log base 3 of 1 equals y, then 3 to the log base 1 is going to equal 3 to the y. Okay? Using that base property. So here, anytime you have an exponential and a log base that are the same, evaluating one another, those cancel. So I'm left with 1 is equal to 3 to the y power. Now here, if I want to solve this like the other one, I need to be able to write both of these with the same base. So notice I can't raise 1 to any power and it equal 3 or 3 to something, right? 1 to any power is 1. So I'm going to think about writing them both with base 3. If I want to write this as 3 to some power, what power of 3 gives me 1? Okay, the only power I can raise 3 to and get 1 is 0. 3 to the 0 power equals 1. Okay, so that means once I drop my 3's, that y equals 0. Okay, so we use the exponential to undo the log and then simplify what's left. Same things on these next ones. Okay, I'm just going to set it equal to y. I'm going to get rid of log base 2 by using exponential base 2. When I use exponential base 2, my log base 2 cancels, and I'm left with 1/2 is equal to 2 to the y power. Okay. Here on the left hand side, I'm going to change this fraction because 1/2 is the same as 1 over 2 to the first power. And then I'm going to use my rules of exponents to move this guy up to the top. When I move him across the fraction line, remember that changes the sign of the exponent. So this becomes 2 to the negative 1 power. 2 to the negative 1 power equals 2 to the y. I can cancel my 2's, which gives me y is equal to negative 1. Okay, let's look at one more and then I'll have y'all try some. Here when I do log base 3 of 27, I'm just going to set it equal to y. To get rid of log base 3, I'm going to use exponential base 3 so that they cancel. 3 and log base 3 and exponential base 3 cancel, and I'm left with 27 is equal to 3 to the y power. Okay, 27 is a power of 3, right? 27 is the same as 3 cubed. If you're not sure, you can go over here to the side and prime factor 27. 27 is 3 times 9. 9 is 3 times 3. So notice here I had 3 copies of a 3, so 27 is 3 cubed. 3 cubed equals 3 to the y, which means when I cancel my 3's, that y equals 3. Okay? All right, so there are 2 for you to try. I'll give you just a minute and then we'll go over them. Okay, so on the first one, I set it equal to y. To get rid of log base 2, I use exponential base 2, raise my equation up into the exponent. My log base 2 and exponential base 2 cancel, which leave me with 2 is equal to 2 to the y power. Now 2 here has an invisible exponent of 1, so I went ahead and wrote the 1 in, so that when I drop my 2's, I know that y equals 1. Okay. On my second example here, to get rid of log base 1/3, I'm going to use exponential base 1/3, raise my equation up into the exponent. So my exponential base 1/3 and log base 1/3 cancel, and I'm left with 1/9 is equal to 1/3 to the y power. Okay, here I can write both sides using exponential base 1/3 because 1/9 is the same as 1/3 squared. Okay, so once I have it written like that, notice I can drop my 1/3 and I'm left with y equals 2. Okay. If you moved the 3 and the 9 to the top and had negative exponents and all that and broke it down further, that's completely fine. You should get the same answer. Okay. All right. So on this next one, it says we want to write the following equations in exponential forms. And I'm going to mark out 2 methods because we're not doing the 2 methods. Okay. I'll show you what the other method is, but it's not really a method as much as it is a shortcut that a lot of people usually don't remember. So I'll show it to you, but don't put a lot of weight on it. All right, so same thing here. Here we already have an equation. We don't have to set it equal to y. It's already equal to something, and we just want to write it in exponential form. So again, to get rid of the log, we use exponential base that matches our log base. So I'm going to use exponential base 2 on both sides so that my log 2 and exponential base 2 cancel, and I get 1/8 is equal to 2 to the -3. And here there's nothing to solve. They just wanted us to write this statement as an exponential statement rather than a log statement. So we leave it just like that. Okay, the other method that we talked about that it says use 2 methods is if you have log base 2 of 1/8 is equal to -3. A lot of instructors will teach you this little shortcut that you take the base, raised to the equal side, gives you the inside number. So in other words, 2 raised to the -3 equals 1/8. So notice we get the same thing using either method. What I find is that a lot of students forget what raised to what equals what. Okay, so if you're not good at remembering shortcuts, go ahead and use the inverse operation. So if you have a log, take the exponential. If you have an exponential, take the log. Okay, so let's go ahead and do the second example here. I have log base 3 of 15 equals b. So again, to get rid of log base 3, I'm going to use exponential base 3. My 3 and my log base 3 cancel, so I'm left with 15 is equal to 3 to the b power. And again, I'm not actually solving here. They just want me to write it in exponential form. Okay, so I'm just going to leave it like that. I'll go ahead and show you the shortcut again in case you are a shortcut person. Okay, if it's written like this, you do the base raised to the equal side number gives you the inside number. So this means 3 to the b equals 15. Okay, so either way. All right, now what's a little bit trickier, here it says use both methods. I'm not going to use both methods in this direction because it's a lot harder for people to think through, okay, if this to that power gave me this, then this number should be my base, this number should be my equal sign, this number should be my inside. If you can think of it backwards like that using the shortcut, that's fine. I'm going to use the inverse operation here. So I have exponentials and I want them written in logarithmic form. If I want them written in logarithmic form, then I take the log of both sides. So here my exponent base is x. So to get rid of exponential base x, I'm going to take log base x of both sides. So I have log base x of x cubed equals log base x of 27. And then log base x and x are inverse functions, so those cancel, and I'm left with 3 is equal to log base x of 27. Okay, and I can leave it like that. If you are a shortcut person, okay, notice our x raised to the third gives us 27, which is what we started with. Okay, so if you want, you can write this out. You know that you should have something like log base x, because that was your original base, of some number equals some number. Okay, so we do x raised to this power, so if it's x to the third, the 3 goes over here, equals the inside number, which is 27. Okay, so if you want to do that reverse thinking and use the shortcut to get it into log form, you can. I highly suggest you just work it out using the inverse operation. Okay, so this one, again, I'm just going to do using the inverse here. So to get rid of exponential base 2, I'm going to take log base 2 of both sides. Okay, log base 2 of 11. So on the left-hand side, my log base 2 and my 2 cancel, and I'm left with e to the x is equal to log base 2 of 11. Now I'm not done because I still have an exponential base here. I still have e to the x. So remember, to get rid of e to the x, I need log base e. So I'm going to take log base e of e to the x, and I'm going to take log base e of log base 2 of 11. Okay, so on the left-hand side, my log base e and e cancel, and I'm left with x is equal to log base e of log base 2 evaluated at 11. Now, log base e, remember, was our natural log. So I'm just going to put over here, note, log base e of x is the same thing as ln x. So anytime you have log base e, we don't leave it written like that in our answer. We go ahead and put ln in. So that means we have x is equal to ln of log base 2 of 11. Okay, ln undoes e. So if you want to write it as log base e when you're working it out, you can, or if you want to just get used to ln being the inverse of e, you can just take ln of both sides. Okay. All right. So those are some of our properties. What I want to look at now is graphing these functions. In order to graph them, we're going to use that same idea of logs and exponentials being inverses. Remember, we did some problems where it said something like if s is -1, 2, and 7, 9. Okay, pretend that's our set. Then to find our inverse, okay, remember all we had to do was swap our ordered pairs. So in the inverse, it would be the 0.2, -1, and the 0.97. Okay, so we're going to use this idea of inverses in that if we know all the ordered pairs of our original function, in order to get the inverse, we just swap all the x's and y's, and that gives us our inverse function. Okay, we don't know how to graph logs, but we do know how to graph their inverses. So what we're going to do is we're going to create a table of values for the inverse function, and then get the log function by swapping. Okay, so I'm going to go ahead and write that out. So we're going to use the inverse of the log, which remember our inverse is our exponential. Okay, or let's say exponential form of the log. Okay, we're going to use the inverse of the log, which is our exponential form, to create an XY table. Then we're going to swap the X's and Y's to get an XY table for the log. Okay. So we're going to create an XY table using the inverse form, which is our exponential, and then we just swap all our X's and Y's, and that gives us a table of values for the log function. Okay, so let's look at a couple examples. If a is greater than 1, so this is an example with a log base that's bigger than 1. So here we chose x, or we chose log base 2 of x. Okay, so here I'm going to go ahead and write, if we're going to use log base 2 of x, then that means that the inverse, oh, I can't write today. That means that the inverse here would be y equals 2 to the x. Okay, so what I'm going to do is I'm going to start out. Notice I'm using the same base. Whatever this base is, that's the base I use in my exponential. Okay, so I'm going to use my exponential base, excuse me, 2 to the x, and create an xy table. And then I'm going to swap all the values to get a log table. So if I take 2 to the x and I raise it to the negative 2 power, so 2 to the negative 2. 2 to the 2 gives me 4. Since there's a negative exponent, that flips it and gives me 1/4. Remember, 2 to the negative 2, this is the same as 1 over 2 squared, which gives me 1/4. So you can apply that exponent and just know when it's negative, it flips it. Okay, 2 to the negative 1 would move that 2 to the bottom, which would give me 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. Okay, so this is my exponential function. So I'm going to go ahead and graph it really quick just so we can see. At negative 2, I'm at 1/4. At negative 1, I'm at 1/2. At 0, I'm at 1. At 1, I'm up at 2. And at 2, I'm up at 4. So this is what my exponential function looks like. We did these last time, so we know what they look like. Okay, there's an asymptote at y equals 0. So now I want to see what happens when I swap and get my log function. Okay, so here I'm just going to say swap. When I swap all my ordered pairs, I now have 1/4 negative 2, 1/2 negative 1, 1 0, 2 1, and 4 2. Okay, so once I swap all of them, I'm going to graph that, and that will give me my log function. So at 1/4, I'm at negative 2. At 1/2, I am at negative 1. At 0, I'm at 1. At 2, at 1, I'm at 0. At 2, I'm up at 1. And at 4, I'm up at 2. Okay, so notice our log function looks like this. So this is log base 2 of x. I'm going to go ahead and write up here my exponential. This was this was 2 to the x. Making up my own values. Okay, one thing I do want to point out is notice anytime you have an exponential and its inverse, so an exponential and a log, they should always be reflected across the y equals x line. So notice this is the identity line, right? So I'm just going to say inverses reflect across the line y equals x. So notice if I copied this black line across that dotted purple line, that's how I get my inverse. And the reason it reflects across the y equals x line is because I'm just swapping all of my x's and all of my y's. So whatever was a y for an x point is now an x for a y point. Does that make sense? So I'm not going to ask you that on a test or anything, but you should know that anytime you graph a function and its inverse, it should be a reflection across this line. If it's not, you did something wrong. Okay, so now I want to talk about asymptotes. Excuse me. Whenever you have an asymptote on your original function, notice when I invert it, okay, or I swap all my x's and y's, I should still have an asymptote. So when I look at my original 2 to the x function, my asymptote was at y equals 0. So if y equals 0 is my problem area, then when I swap all my x's and y's, now x equals 0 is going to be my problem area. So notice as this blue function heads down, it's never going to touch or cross the y equals x line, okay? Which means that we have an asymptote at x equals 0. Okay, so all exponentials have an asymptote, which means that when you flip it and get a log function, all log functions will have an asymptote. Okay, so I'm going to go ahead and write domain and range here, and then we'll look at another one, just getting the points down. So my domain here, the furthest to the right I can go is 0, and I'm not going to include it because it can't touch or cross that 0 line because of the asymptote. Okay, and then the range, notice this blue picture is going to keep going down. It's also going to keep going up. So negative infinity to infinity. Okay, let's look at another one. This next one is a base example where our log base is between 0 and 1. If our log base is between 0 and 1, we still work it the same way. We look at our original base down here. So notice my original base was 1/3, log base 1/3 of x. So when I get my exponential base, I use the same one. So my inverse here would be y equals 1/3 to the x. So I'm going to find my ordered pairs using 1/3 to the x and then swap them to get log base 1/3. Okay? So 1/3 to the -2. I square it and I flip it. If I square it, I get 1/9. When I flip it, that becomes 9. 1/3 to the -1. 1/3 to the 1 is 1/3. When I flip it, it becomes 3. 1/3 to the 0 is 1. 1/3 to the first power is 1/3. 1/3 squared is 1/9. Okay. So here I have all my values. So I'm going to swap them to get my log function. Okay. When I swap them, I now have 9, -2, 3, -1, 1, 0, 1/3, and 1/9. So I'm going to go ahead and come down here and graph both of them just so that we can see that they reflect across that identity line. When I graph my exponential at -2, I'm up at 9. Okay. At -1, I'm up at 3. At 0, I'm at 1. At 1, I'm at 1/3. And at 2, I'm at 1/9. Okay, so my exponential function looks something like this. Okay, notice asymptote at y equals 0. And then whenever I swap those ordered pairs, that means when x is out at 9, I'm down at -2. When x is 3, I'm down at -1. When x is 1, I'm at 0. When x is 1/3, I'm up at 1. And when x is 1/9, I'm up at 2. Okay, so notice this blue log function line here, this is log base 1/3 x, is a perfect reflection across the identity line of its exponential counterpart. Okay. Let me go ahead and write my identity line here. Okay, so notice it's a reflection. If I reflect the black line across the purple line, I get the blue line. If I reflect the blue line across the purple line, I get the black line. Okay, so now I want to look at, I had an asymptote at y equals 0. Notice when I reflect it, now I should have an asymptote at x equals 0 because that blue line is never going to touch or cross the x equals 0 line. It's going to get closer and closer in like tiny little fractions, but never touch it. So that means that we have an asymptote at x equals 0. Okay. So I'm going to go ahead and find domain and range. Again, my blue function can go all the way to 0 to the left, but not touch or cross it, so we use a parenthesis. To the right, it's going to keep going on out to positive infinity. My range, it's going to keep going low, and it's going to keep going high, so negative infinity to positive infinity. So notice both log functions start off crossing at the point 0, 1, and they both have vertical asymptotes at x equals 0. So every parent log function that we have, that should hold true. They should all cross at 0, 1, and they should all have a vertical asymptote at x equals 0. So what we're going to do now is we're going to take these and we're going to start transforming them. Okay, so what we just did here is how we're going to start it. We're going to look at the inverse function to get our table of values. Then we're going to swap it to get the log parent function. And then once we have the log parent function, then we can do our transformations to see what our new function looks like. Okay? Okay, so on the top of this page, it says transformations of exponential functions. It's the same process as the section 4.4 or E4.4, which is where we did HSRV. Okay, and we're going to get our starting points in our XY table from the exponential form of the parent function. Okay, so I'm just going to do an example so that you see, and then we'll talk more about it, okay, as we do it. So here we want to find the following functions, list the transformations, graph the results, state the domain and range, and also the location of the asymptote. Okay, so before I even get started, before I even look for any transformations, what I want to look for is what is my parent function. So I look at the little base here, okay, which is a 3. I have log base 3. So in order to graph log base 3, I'm going to look at it in its exponential form, meaning I'm going to look at 3 to the x. Okay, so I'm going to go ahead and write here my exponential parent function is going to be 3 to the x. So I'm going to make a table of values, and actually I'm going to rewrite that because that looks horrible. Okay, so I'm going to use 3 to the x, and I'm going to go ahead and write over here, this is where we get our parent function. Okay, so this is our exponential parent, which on the worksheet that you have that correlates to this section, it'll ask you for both the exponential parent and the log parent, so make sure you know which one's which. Okay, so 3 to the x is our exponential parent, and so I'm going to go ahead and plug in -2, -1, 0, 1, and 2. Now on a lot of these you really only need 3 points. If you just wanted to do -2, 0, 2, that's fine. The more points you get, the better shape you get. So if you're a little iffy on the shape, go ahead and do it the 4 points. Okay. If I do 3 to the -2 power, okay, when I square 3, that gives me 9, and then the negative flips it, so that would give me 1/9. 3 to the -1 is 1/3. 3 to the 0 is 1. 3 to the first power is 3, and 3 squared is 9. So that's my exponential form of this function. Now I want to swap all my variables to get it, in my log form. So I'm going to get log base 3 of x by taking my exponential parent and swapping all the ordered pairs. So I'm just going to say swap. So to go from this table to this table, I'm just swapping all my ordered pairs. Okay, so now I have 1/9 -2, 1/3 -1, 1, 0, 3, 1, and 2, 9. Now, once I have my log parent, which is what I have here in blue, I no longer care about the exponential parent. Okay, I only care about the log parent and the end result. So to see what my original log parent looks like, I'm going to go ahead and graph it, and then we'll look at what transformations have happened. So at 1/9, I'm down at -2. At 1/3, I'm at -1. At at 1, I'm at 0. At 3, I'm up at 1. And at 2, oh, whoops, I didn't swap those last ones. Sorry. Instead of 2, 9, that should be 9, 2. So out at 9, I'm up at 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, up at 2. Okay, so this is what my original, this is what my original log function looks like. And now I want to see what transformations have happened. Okay, so as it is, notice we have that vertical asymptote at x equals 0, and now we want to see how it's changed. So I look at the transformations. The only one that I have is a -1 here. When I have a -1 and it's happening inside the log parentheses, that means it's being applied to the x, because x's are inside the function. Okay, and when I subtract 1, remember our x's are backwards, this is actually going to move us to the right 1. Okay, when I move to the right 1, I'm going to add 1 to my x's. Okay, that's the only transformation that has made this function look different from the blue parent function that I just created. Okay, so there's no other transformations, so I'm going to go ahead and do my one transformation, which is to move right 1. To move right 1, all I have to do is add 1 to the x's from the previous table. So 1/9 plus 1 is 1 1/9. 1/3 plus 1 is 1 1/3. 1 plus 1 is 2, 3 plus 1 is 4, and 9 plus 1 is 10. My y's stay the same. So -2, -1, 0, 1, and 2. Okay. So now I'm going to go ahead and graph my new function, which says at 1 1/9 I'm at -2. At 1 1/3 I'm at -1. At 2 I'm at 0. At 4 I'm at 1. Excuse me. And at 10 I'm up at 2. So notice what has happened between my blue line and now my new pink function here is that it has in fact shifted to the right 1 unit. Okay, so notice if my vertical asymptote was at x equals 0, okay, and my graph was approaching it, then that means if I shift the whole thing to the right 1, now my vertical asymptote is going to be at x equals 1. Okay, so I'm going to go ahead and draw that in. Okay, so I have an asymptote at x equals 1. Okay, and then I'm going to go ahead and write my domain and range based on my new pink function. So notice the furthest to the left I can go on this picture is 1, and I'm going to use a parenthesis because it won't ever touch or cross that asymptote line. And then it keeps going out to the right, so from 1 to positive infinity. And then my range is going to be from negative infinity to positive infinity because it's going to keep going down, getting closer to that asymptote, and it's going to keep going up. Okay. All right, so let's look at another one. Now you see the process. We look at our little log base. Whatever that number is, we do that number raised to the x power to get the exponential parent. Once we have created a table of values using the exponential parent, we swap it, and that gives us the log parent. Okay. I always graph the log parent so that I see what the original shape looked like, and then I do my transformations. Okay. On your worksheet, if you don't graph the log parent, that's fine. You can just graph the end result. However, it does help to make sure your shape looks right if you do the parent. Up to you. Okay. All right, let's look at another one. So this one is m of x equals log base 1/2 of 1 minus x. And the first thing I'm going to do is rewrite this because I hate it when they don't write the x first inside the parentheses. It really doesn't matter, but it bothers me. So I'm going to write this as m of x is equal to log base 1/2 of negative x plus 1. Writing it in the correct order helps me to see the transformations. Okay, if you're fine with the way it was written before, that's completely fine. So I identify my exponential parent by just looking at what is the log base. Okay, so that tells me my parent. So I'm going to go ahead and create a table using my exponential parent, which in this case is 1/2 to the x power. Again, you really only need 3 points. You could do like -202, -303, that kind of thing. I'm going to be more accurate and do -2, -1, 0, 1, and 2 so that we get a good picture. When I do 1/2 to the -2 power, the negative flips it, which makes it 2 over 1, which is just 2, and 2 squared is 4. Same thing with the -1, the negative flips it, which makes it 2 over 1, which is just 2. 2 to the first power is 2. Anything raised to the 0 power is 1. 1/2 to the first power is 1/2. 1/2 squared is 1/4. Okay, so this is my exponential. So now I'm going to swap that table, swap all my ordered pairs, which will give me my log parent, which looks like log base 1/2 of x. Okay. Notice my exponential and my log always have the exact same base. The only difference is their x's and y's are swapped. Okay. So I'm just going to put down here swap. Go from this table to this table, I swap, which gives me the ordered pairs 4, -2, 2, -1, 1, 0, 1/2, 1, and 1/4, 2. So now that I have my log parent function, I'm going to go ahead and graph it so I can see what the general shape is. So it says when x is 4, 1, 2, 3, 4, I'm down at -2. When x is 2, I'm down at -1. When x is 1, I'm at 0. When x is 1/2, I'm up at 1. And when x is 1/4, I'm up at 2. So this is what my original, it's not a very curvy line. This is what my original log function looks like. Now what I want to do is identify what transformations have happened. So notice if I look at my function up here, I have two things happening inside the log. The first thing I see is I have this negative sign on my x's. If I'm negating my x's, that's a reflection about the y-axis. So a reflection about the y-axis, I negate my x's. Okay? And then I also have a plus 1. Plus 1 on the inside of the function affects the x, which moves me left and right. Okay? Since it's an addition and our x's are backwards, this is actually going to move me left 1. So I'm going to subtract 1 from my x's. There's no stretching because there's no multiplication, and there's no vertical shifts because I'm not adding or subtracting outside the log function. Okay? All right, so I need to do two tables to modify my function. The first one is my horizontal shift, so that will make it look like log base 2 of x plus 1. Okay. To move it to the left 1, I'm going to take my x's from the previous table and subtract 1. So 4 minus 1 is 3, 2 minus 1 is 1, 1 minus 1 is 0, 1/2 minus 1 is negative 1/2, and 1/4 minus 1 is negative 3/4. Okay, my y's stay the same. So negative 2, negative 1, 0, 1, and 2. Then my last transformation table will be to reflect about the y-axis. So now my function looks the way I want it to, log base 1/2 of negative x plus 1. Whoops, and I wrote 2 instead of 1/2 on the last table, sorry. Log base 1/2. Okay. So to get that reflection, all I'm going to do is take my x's from the previous table and negate them or change their signs. So I get negative 3, negative 1, 0, 1/2, 3/4, and then my y's stay the same. Negative 2, negative 1, 0, 1, and 2. Okay? So I'm going to go ahead and graph my new function, which says when x is negative 3, 2, 3, I'm down at negative 2. When x is at negative 1, I'm down at negative 1. When x is 0, y is 0. When x is 1/2, I'm up at 1. And when x is 3/4, I'm up at 2. So notice if I connect my dots, it should look something like this. Now, if you're confused about where your asymptote is, think about how your picture has changed. Okay, so notice we started with the blue picture. We started with the blue picture, which is approaching x equals 0. Okay, and then we moved it to the left 1. If we move it to the left 1, it should now be approaching x equals negative 1, right? It was 0, and we moved it left 1, so now it's approaching negative 1, and then we rotated it about the y-axis. So instead of approaching negative 1, when we flip it around, it should now be approaching positive 1. So make sure you draw that in on your graph, and make sure when you draw your graph, your line doesn't cross the asymptote. Okay, so here we have an asymptote at x equals positive 1. Okay, so that means that my domain would be from positive, I'm sorry, I go to the left first. The farthest to the left I can go is negative infinity. Farthest to the right I can go is 1. And I use a parenthesis because it's never going to touch or cross 1. And then for my range is all real numbers. It's going to keep going down, it's going to keep going up. Okay, are we kind of okay? Let's keep going. Let me look at a couple. Oh no, just one more. Let me look at one more and then I will have y'all try some. Okay. First thing I do is identify the exponential form of the parent function. And this is another one that I feel like it's written retarded. Okay, I like my function to come first and my constants last. So I'm going to rewrite this as p of x is equal to negative log base 2 of x plus 1 plus 3. I like the 3 on the other side. If it doesn't bother you, leave it as it is. Okay. I look at my log base number and that tells me what my parent is. Okay, so here my parent, I'm going to start with 2 to the x power. I go ahead and put my points in here. So negative 2, negative 1, 0, 1, and 2. When I raise 2 to the negative 2, I'm going to get 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. Okay? Then I'm going to swap my table to get my parent log function, which is log base 2 of x. Okay? So all I'm going to do is swap my values. Swap. So I get 1/4 negative 2, 1/2 negative 1, 1, 0, 2, 1, and 4, 2. Okay. So now that I have my log parent function, I'm going to go ahead and graph it. So at 1/4, I'm down at negative 2. At 1/2, I'm at negative 1. At 1, I'm at 0. At 2, I'm up at 1. And at 4, I'm up at 2. So this is what my original log parent function looks like, approaching x equals 0. Okay, now let's look and see what transformations have happened. I have 3. I have a negative outside the log, I have a +1 inside the log, and I have a +3 outside the log. So I'm just going to go in that order. Negative log, okay? Negatives are reflections. Here, since the negative is outside the function, it's negating the y's. If it's negating the y's, then this is a reflection about the x-axis. So I'm just going to write negate y's. Okay, the +1 on the inside affects the x. X's are backwards, so a +1 tells us to go left 1. So I'm going to subtract 1 from my x's. And then the +3 is on the outside of the function, so that's a vertical shift either up or down. Because it's a +3, that means we're going up 3. So I'm going to add 3 to my y's. There's no stretching or compressing because there's no multiplication. All right, so the first one, remember you have to do these in HSRV order or your graph doesn't turn out right. So the first thing we do is our horizontal shift. So now it looks like log base 2 of x plus 1. To move it to the left 1, I'm going to take my x's from the previous table and subtract 1. So 1/4 minus 1 is negative 3/4. 1/2 minus 1 is negative 1/2. 1 minus 1 is 0, 2 minus 1 is 1, 4 minus 1 is 3. My y's stay the same. Negative 2, negative 1, 0, 1, 2. The next shift I do is a reflection about the x-axis. So now my function looks like negative log base 2 of x plus 1. Okay. To get that reflection, I negate my y's. So I'm going to take my y's from the previous table and negate them. So now they become positive 2, positive 1, 0, negative 1, negative 2. My x's stay the same, so they are still negative 3/4, negative 1/2, 0, 1, and 3. And then the last transformation I need to do is move it up 3. So now my function looks like negative log base 2 of x plus 1 plus 3. And that's all of them. So whatever I get for this table, that's going to be what I graph. Okay, so I'm going to take my y's from the previous table and add 3. So my x's stay the same, negative 3/4, negative 1/2, 0, 1, and 3. When I add 3 to each of my y's, 2 plus 3 is 5, 1 plus 3 is 4, 0 plus 3 is 3, negative 1 plus 3 is 2, and negative 2 plus 3 is 1. So I'm going to go ahead and graph my new points and see if I can figure out this shape. So at negative 3/4, I'm up at 5. 1, 2, 3, 4, 5. At negative 1/2, I'm at 4. At 0, I'm at 3. At 1, I'm up at 2. At 3, I'm up at 1. 1, 2, 3, 1. Okay, so I can see the general shape. If you're not sure where your asymptote is, think about your problem. You started with this blue log that's approaching x equals 0 in the negative direction. Okay, so the first thing we did is move left 1. When I move it left 1, now instead of approaching 0, it's going to be approaching negative 1. Okay, and then I reflected about the x-axis. So instead of approaching negative 1 from the bottom, now when I flip it, it's going to be approaching negative 1 from the top. Okay, and then I move it up 3. So it's still going to be approaching negative 1, but it's coming up, excuse me, higher. So I'm going to go ahead and draw in my asymptote. And say I have an asymptote at x equals negative 1. which means that my domain, the furthest I can go to the left, is -1, and then it's going to continue to go out to positive infinity. My range, again, is unrestricted, so -infinity to infinity. Okay. All right, so there is, I think, 3. Let me see really quick. 1, 2, nope, just 2. There's 2 for y'all to try. I'll give you just a minute, and then we'll go over them. Okay. All right, so on this first one, our parent function is 1/2 to the x. So I made a table for that, and we swap all the ordered pairs, which gives us our parent log function, which is log base 1/2 of x. So I graphed that in blue. And then notice here our only transformation was to go right 3. Now when we move left and right, that changes our asymptote. So if we start at 0 and move it to the right 3, now our asymptote should be at 3. Okay, so I graphed our pink result here, which means that our domain would be 3 to infinity. Our range -infinity to infinity. Okay, asymptote at x equals 3. Let's look at the second one. On the second one, we look at the log base, which here is 5. So I start with 5 to the x, that's my exponential parent. Make a table of values. Now notice here I was doing -2, -1, 0, 1, and 2. When I plug 2 in, I get the point 225, which is not on this graph. So I went ahead and marked it off because there's no need for me to transform that point. Because unless I'm going to severely decrease my y's, that point won't end up being on my graph. So I just X that out, so that if you're wondering why I crossed that out, that's why. Okay, I swap all my ordered pairs, which gives me my log parent function, which here is log base 5 of x. I went ahead and graphed that here in blue. Notice asymptote at 0. Then I went left 2. Now when you move it left 2, that moves your asymptote from 0 back to -2. And then I just went down 1. Down doesn't affect my asymptote, so it's still approaching -2. So here my final result is graphed here in pink, approaching x equals -2, so that's where my asymptote is, and I forgot to write that in. I should do that. Asymptote at x equals -2, which means that my domain is from -2 to infinity, and my range is -infinity to infinity. Okay? All right, so the graphing hasn't been that much different. I mean, pretty much the only thing that has changed here is we have to start out with the exponential function and then swap all the ordered pairs to get our log function. But once we get our log table of values, all this HSRV and graphing is exactly the same as it was with exponentials, right? We have to be aware of where our asymptote is, and we have to do one table for each of our transformations. So the only new thing is starting off with our exponential form, swapping it to get our log form, and then the same process we've been doing. Okay. I want to just review some more of properties of logs. We use these when we did the examples at the beginning of this section. The only difference is we were actually solving using the definition rather than the shortcut. I talked about how I'll show you the shortcut, but I really don't want you to use it. So I am going to use the definition of log to show you why each of these work, and then we'll look at solving some, whichever way makes more sense. So remember, when we have logs, I'm just going to put up here, recall, if we have log base a of x equals y, then that means a to the y equals x. So if you recall our little silly shortcut, it was whatever our little base is raised to the equal side gives us the inside number. Okay, so that's how I got this, a to the y equals x. So that's what I'm going to show to prove this. Now before I do that, I'm just going to show you again how we get that. If I have log base a of x equals y, to get rid of log base a, we use big exponential A and move our equation up into the exponent. And then notice log base a and exponential base a cancel. And so I have a to the y equals x, which is what I have up here. So whether you work it out using the definition or you're working out using it, the fact that they're inverse functions, it doesn't matter as long as you are consistent with your method of choice. Okay, so that's where it comes from. I'm going to go ahead and erase that so I can give some reasoning for each of these. So using this little shortcut just for this one little part, the reason log base a of 1 equals 0 is because a to the 0 power equals 0. No matter what our base is, the only way that we can raise that base to some power and end up with a 1 is if it's 0. Okay? Same thing here. If I do my little trick, a raised to the first power gives me a to the first power, right? So this is because a to the 1 equals a. On the next one, same thing. If I raise my little base to the equal side, that should give me the inside. So again, because a to the x equals a to the x, pretty easy. Now, some of y'all don't use the shortcut. Doing the little base raised to the equal side gives us the inside number. The other thing we looked at is we know that if we have log base a of an exponential, those are inverse functions, so they cancel. So the other way you can look at this is if I have log base a of a, those cancel and I'm left with whatever's exponent is on the a. So here, this was an a to the first, this was an a to the first power. So if I cancel the log base a of a, I'm left with 1. Same thing is true on my third bullet here. Log base a of a cancels and I'm left with just the x from the exponent. Okay? Now, these two rules are pretty much the same thing. They're saying that an exponential base and a log base that match when evaluating one another cancel. So if I have log base a evaluating a, they cancel, like the last two I just marked out. This fourth bullet saying the same thing, but it's saying if we have exponential base a and then up in our exponent we have log base a, the same thing is true. These will cancel and I'll just be left with the x. So the idea to simplify these is to either, if there were given a log, to take the exponential form so that I can cancel those, or if we're giving something that's an exponential form, I can take the log with that same base to cancel that out. Okay, so I'm just going to say here, because log base a of x and a to the x are inverse functions. Okay, so and then I'm just going to erase this so we can still see what's written there. Okay, so what we're going to do now is just look at a few examples, and we're going to try to use this idea of if we can get the log base and the inside number base to match, then we can easily just cancel those out and keep what's left in the exponent. Now, if we're not able to do that, sometimes it's a little bit easier to just set it equal to y and solve. So you'll see what I mean. Let's look at these 4 little examples. All right, so the first one is log base 9 of 1 over 81. So I noticed right away with log base 9, I know I can write 81 with an exponential base 9, right? I could write this as log base 9 of 1 over 81 is the same as 9 squared. Okay, now I can't cancel out log base 9 and 9 right here because I don't have a 9 as my inside number. I have a 1/9. Okay, so what I'm going to do is use my rules of exponents to move this 9 squared up to the top. Now when I move it up, it's going to become 9 to the negative 2, right? So what I have now is log base 9 of 9 to the negative 2 power. But the good thing about that is now my log base and my inside number base match. They're both 9s. So using my rule up here, this third bullet, okay, log base a of a to the x, I can cancel those and I'm left with whatever's in the exponent. So these will cancel and this whole thing just equals negative 2. Okay. Let's look at another one to the right here. If I move to the right, I just have log. Now, when there's not a number written here, that means that this is a common log. And when it's a common log, that means that it's an implied base 10. Okay, so I'm going to rewrite this as log base 10. Now, if I want to cancel out base 10, I want to be able to write this number as 10 to some power. Okay, if you're not good with going from 10 to some power in decimal places, I'm going to go back old school and count it out and write it as a fraction. So remember, our first decimal places are tenths, then our hundredths, then our thousandths, then our 10,000ths. So right now I have 1/10,000th. Okay, now 10,000 I can write as 10 to some power. So I'm going to go ahead and write this as log base 10 of 1 over 10 to the, we count the zeros, there's 4 zeros here, so this is the same as 10 to the 4th. And then from here I'm going to solve it the same way I did the last one. I'm going to move that 10 to the 4th up to the numerator. Anytime I take a base across the fraction line, it changes the sign of the exponent. So this becomes 10 to the negative 4. So now I have log base 10 of 10 to the negative 4. Now my bases match. Now I can cancel my log base and my exponential base, which means this guy just equals negative 4. Okay, let's look at a couple more. On this next one, I have log base 1 over 16 of 4. Now, some of you may have enough math knowledge to know how to write 4 as 1 over 16 to some power. But that's a little bit backwards thinking than what we've been doing here. So instead of trying to write 4 as 1 over 16 to some power, what I'm going to do is I'm just going to go ahead and say this equals y. And then I'm going to try to solve for what y must be. Okay? So I can get rid of this log base 1 over 16 by raising my equation up into the exponent using exponential base 1 over 16. Whoops, I got 1 over 6. 1 over 16. So that way on the left-hand side, my exponential base 1 over 16 and my log base 1 over 16 cancel. And what I'll be left with is 4 is equal to 1 over 16 to the y power. Okay. Now I can manipulate this because I know 16 is a power of 4, right? This is the same as 4 is equal to 1 over 4 squared raised to the y. Okay. And then using the same idea I did before, I'm going to move my 4 to the top. When I move my 4 to the top, it becomes 4 to the negative 2. Okay. So now I have 4 is equal to 4 to the negative 2 raised to the y power. Now, anytime I have a power raised to another power, I multiply those exponents. So this tells me 4 is equal to 4 to the negative 2y. Now, using that base exponent property that I have, as long as the bases are the same, I can drop them and just set the exponents equal. So notice what I have is 4 to the first power equals 4 to the negative 2y. So I can drop the 4's and be left with 1 is equal to negative 2y. When I divide off my negative 2, that tells me that y is equal to negative 1/2. Okay, so that one took a little bit more work, but it's the same idea. Okay, same process. Let's look at this next one. This next one's the same thing. Notice I see ln and I see e. I really want to be able to get those two things together because remember ln is log base e. So if I can get it to where it's like log base e of e to some power, then I can cancel those. So what I'm going to do is write the 5th root of e with rational exponents. Now I don't know if you went over this in your previous math class, so I'm going to give you a quick little refresher. If you have anything like the nth root of a to the m power, this is the same thing. Actually, let me use a different color so we don't think that that goes with the last problem. If you have something like the nth root of a to the m power, this is the same thing as a to the m over n. Okay, so notice what we're doing is we're doing power over root. So we can write any radical with a fraction exponent or a rational exponent by doing the power over the root. So if I want to write my problem here with a rational exponent, notice I have e to the first power and I'm taking the 5th root of it. So this is the same thing as ln of e to the power over root. So 1 over 5th power. Power, I have 1 copy of e over root, I'm taking the 5th root. Okay, and now my ln and my e are side by side. Since they're inverse functions, I can cancel them, and this just equals 1/5. Okay? All right, so that is the end of E4.2. You have a regular My Math Lab assignment for E4.2, and you also have a worksheet that needs to be worked by hand, scanned and emailed, or faxed to me. If you have any questions, please let me know. Okay?